Hello physics students. So in the last video, you learned the law of reflection, and we used the law of reflection to understand why we see a replica of this coin or any object placed in front of a flat mirror inside the mirror behind the mirror. The way we would achieve that is through some basic principles of ray tracing. So this coin is sending out light in all directions through diffuse reflection when the light fixture is illuminated. So we imagine two rays. Maybe one is going like this, hits the mirror. It will obey the law of reflection at this point. In other words, if we draw a normal like this and then reflect this to the opposite side of the normal, this would be the ray reflected from the mirror. We could do that for one other ray. We could do it for many rays if we wanted to, but all we need is one more. Let's suppose we've got a ray that comes in and hits the mirror like this, coming from the coin. It reflects, law of reflection, like this. Now these two rays, they spread out after they hit the mirror. In other words, in optics we say they diverge as they're going away from the mirror. If these rays were to go into our eyes, our brain would think that the coin is wherever these two rays originated from. Well, they originated from here, but our brain would trace these rays straight back, and if you look, these both are aimed at the reflection or the image of the coin, so our brain perceives the coin inside the mirror right there. So that's the kind of physics of how an image is produced. Well, today what we're going to do is we're going to look at more complicated objects, more realistic objects. Like, for example, I'm going to use this little action figure to represent you standing in front of the mirror in the morning. So first thing that you notice, we're just going to look and observe some characteristics of the image compared to the original person, summarize, and then what we're going to do is we're going to see if we could reach those same conclusions if we ray trace for an object that's not just like a dot, like a coin. So the first thing that we observe is that the reflection of the man is right side up. His reflection is not upside down in the mirror. Now that may seem like a silly observation because every time you look in a mirror, you're always right side up, your image is compared to you. But in general, in optics, that's not always true. Some objects like curved mirrors, this is a flat plane mirror, curved mirrors or lenses can produce images that are upside down. One example I could give you, your eyes. If you look at me with your eyes and someone else looked inside your eye, looked at what was on your retina, they would see an exact replica of me upside down. So everything inside your eye on your retina is upside down. Your brain flips it back up so you perceive it in the right orientation. So right side up. The other thing is the man is the image is the same height as the man. So if we were to measure this with a ruler, same image size, 6-foot man, 6-foot reflection. Again, that's obvious from everyday usage of mirrors, but it's not always true with optical objects or devices. Sometimes the image is smaller or bigger. So that's the second point. Another point is that the man is a certain distance in front of the mirror. So you see here, using my pencil as a measuring device, he comes about to the beginning of this clip in front of the mirror. And now if you look inside the mirror, the reflection is the same distance behind. There's a pencil that you should see inside the mirror, and he comes to the same thing, same point, the start of the pencil clip. So if he's 1 meter in front of the mirror, his reflection is 1 meter behind the mirror. So that's the third point. The distances are the same. And the last point I'm going to make is that if he raises his right hand, you may think, well, his right hand is raised in the mirror, right? Because that's the reflection, the arm that's up is on our right side. So what I'm going to do is just put this little drawing here, real simple, to show that that's his original hand orientation. The right hand is up. But if I flip him around to make his reflection, look what happens. Now suddenly, in our perspective, it's his left arm that's up, not the right like the original man standing here. So the reflection What happens was this was up, right? That's what we saw. It matched him in front of the mirror. So when you put your right arm up, your identical twin in the mirror is actually putting their left arm up. So basically everything is reversed in a plane mirror when you're looking at the images. I could verify that by just taking a simple word like this, backwards, and when you look at it in the mirror, it's written backwards because the image reversed these words and made them, well, the word backwards is backwards, okay? Now, another point I want to make is that when we're studying optics, physicists don't draw like figures like this, stick figures or people. It takes too much time. They simplify and they just draw arrows because the arrow, when you're analyzing it, can tell you enough information. Like, for example, if we saw that the image was flipped inside, we would see an upside down arrow. So an arrow has a top and bottom, so it's the simplest way we could use an object, or the simplest object that will show when the object is upside down. So we always draw arrows in optics. Now, what we're going to do today is we're going to ray trace with this, an object like this, and see if we can figure out the correct answer of what the image would look like. We see it here already. We've got an arrow that's sort of not parallel to the mirror. It's tilted towards the mirror. And if you look at the reflection, you see that it's also tilted toward the mirror, but you see that the angle is the opposite way. So this is what the mirror is showing us the image really is. We're going to practice our ray tracing to see if we could figure out this image without even looking at the mirror, just with our law of reflection and ray tracing. So that's what I'm going to do. I'm going to switch the camera and we're going to practice ray tracing for an object like this. So once again, I'm going to do my ray tracing on a desk with a piece of paper because it's more accurate than a chalkboard. So what I want you to do is begin by writing the title for today, Optics 2, Image Location, a Plane Mirror. What I mean by a plane mirror is not one that's not decorated. I mean plane in a mathematical sense. In other words, the mirror is flat in all dimensions. It doesn't have any curvature to it. So go ahead and write this title now. All right, so next we're going to do our ray tracing, but just some points before you start drawing. I'm going to choose the middle-sized protractor out of my little family of protractors here. I think that'll work the best for the ray tracing. I think you should do the same thing. The other thing is, don't skimp on the paper. Draw this very large. If you try and cram this into your notebook without using a protractor, it's going to be a mess. It's not going to really be any instructive for you. You're not going to really learn much from the ray tracing. So draw this at least 10 centimeters. If you don't have a centimeter ruler, then draw it at least 4 inches. I drew mine 12 centimeters, and then I labeled the bottom underneath the mirror. So do the same. Now I'm going to slide this down. The word mirror will disappear because I want this to be filling as much of the screen as possible. Now let me tape this down. And then draw an arrow. Now notice that the arrow is comfortably, all parts of it are further away than the size of the protractor. That's critical because if you put the arrow too close and the arrow starts covering the original arrow, the protractor covers the arrow, you won't be able to do the ray tracing. So have a nice gap. Also tilt it slightly toward the mirror like I had in the example that we just saw with the real mirror. And then label it object. You don't have to use a marker to draw the arrow. You could just use it and use your pencil. By the way, you should be using pencil because if you make a mistake, you could erase. Obviously, pen you cannot. So go ahead and set this up now as I just described. All right, so we know the answer. We know that this is going to create an image like here, a replica like this, an arrow like that. Going this way, tilted in just like this one's tilted in. The same distance behind, the same size, all those things that we just talked about in our in the demonstrations. But how do we do that with ray tracing? What we're essentially going to do is we're going to do ray tracing pretending almost like there are 2 coins here and do ray tracing for each one. 2 rays coming off, bouncing off, extended back, 2 rays coming off, bouncing off, extended back. Where these 2 rays meet is going to be the bottom of the arrow. Where these 2 rays meet back here will be the top of the arrow. So it's basically we're going to be sketching 4 rays. So be ready for all that tedious drawing. Now I told you to use pencil. I'm going to use pen though, because basically I want the different rays to show up in different colors. So what I'm going to do is I am going to take a random ray like this. Does it matter which angle you use? No, it doesn't. As long as it doesn't come dead on. Make it come off to some angle, or you could go like this. The first ray, I'm going to go up to the top of the mirror here like this, at a slight angle, right from the very top, and I'm going to have this come in. This is going to be the first incident ray coming in. Maybe I'll write 1 incident. Okay. Now what I have to do is reflect that ray like we learned how to yesterday. So I'm going to put the protractor, put this little part of the protractor right where the ray hits the mirror, right there. And then I'm going to align this as best as I can. The camera tripod's in the way, so I don't know how good I'll get here, but basically like that. Now I'm going to put, actually maybe I'll use pencil for the normal, a dot for the normal right here. And then what I'm going to do is figure out the angle incident here. So I'm going to count over from the normal. Here's 5 degrees, 6, 7. I guess I get 8.5 is my incident ray. So I'm going to make the reflected ray 8.5 to the other side. So 5, 6, 7, 8.5 right there. Okay, so there are my 2 dots. Hopefully you could see them. Maybe I'll darken them. Darkening makes a little bit inaccurate because then the dot gets bigger. But what I'm going to do now is construct the normal and the reflected ray. So a dotted line for the normal, something like this. Okay, dotted line. And then the reflected ray will go up like this. Now I'm not going to move the ruler away just yet, because remember from yesterday, what happens is our brain's going to receive this light and it's going to keep extending it in our mind backwards. And where the ray meets the other reflected ray is where we'll perceive the head of the arrow. So I'm just going to do this while the ruler was in place. Complete my arrowhead, and I will label this 1 reflected, 1 incident. So go ahead and make the same kind of ray in your notebook now. Go ahead and do that now. All right, now I'm going to do a second ray. I could go up like this, but I'm kind of running out of mirror space, so I'll go this way maybe. And I will go. Again, you don't have to have it any exact angle yet. So this is going to be 2 incident. Now I have to make this ray reflect using the law of reflection in my protractor. So again, I'm going to put this, line the protractor up here at the point of impact, and then hopefully, I can't see it that well because again, the tripod's in the way, but hopefully the bottom of the protractor aligns nicely with the mirror. I think that's pretty good. Maybe I'll try. Okay, so something like that. So I'm going to hold the protractor in place. I'm going to make a mark for the normal. Try and be real precise here. Now what I'm going to do is determine the incident ray angle, the angle of incidence. So I'm beyond 10 degrees, so I go to this dot, that's 10 degrees, and then I'm going to count over 11, 12, a little hard to see, 11, 12, 13.5 degrees is the incident angle. So I'm going to count off 13.5 degrees, the other side of the normal. Here's 10, 11, 12, 13.5 is right around there. All right, that looks pretty good right there. So now I have these dots for the normal and the reflected ray. So let me construct the normal first. There's my normal. And then I'm going to make my reflected ray with pen. Again, I would probably stick with pencil maybe. In case you mess up, you could erase. So that looks pretty good. I will just go like this. Arrowhead there. Now, again, I'm not going to move the ruler yet. What I'm going to do is, because again, my brain, when my eyes receive these, my brain's going to trace these back and it'll see the arrowhead image where the two rays, we say, converge, where they meet together. All right, so I'll go like this and I'll label this 2 reflected. Okay? So what my brain perceives is an image of the arrowhead right here. I'll just put head, because light from the arrowhead came, bounced off, and so it traces back like that. That's what my brain does, sees an image of a head right there. Where's the tail? Well, we know it's here, right? So we already kind of know the answer, but we're going to do that, figure that out with ray tracing. So we need 2 rays here. It's like we're doing another coin problem from yesterday from down here. So, oh, I didn't create a pause. Go ahead and construct this ray to the best of your ability. It doesn't have to be the same angle as me, but it has to be accurate. So go ahead and make that second reflected ray and the trace back. All right, so let's now go and do 2 rays here. I'll go like this. Let's see, that'll go. Okay, yeah, I'll make this maybe a little bit more steep. Why not? But again, the actual angle doesn't matter as long as it's accurately done. All right, so there is, I guess I could call this 3 incident. Now, I will reflect that. So again, I line my protractor up, put where the ray impacts here with that point, and then lined up like this. Again, just do your best. So I'll hold this in place. And now I will mark the normal. And then what I'm going to do is count out how many degrees the incident angle is. So there's 10, that circle, 20, and it looks like right on 25 degrees is that incident angle. So I'm going to go the other way 25 degrees. Here's 10, 20, 5 is right here. Okay, so I have my 2 marks. I will now construct the normal and the reflected ray. Okay, so this is reflected ray 3, so this I could say 3 reflected. But once again, my brain will receive this and ultimately trace or extend this ray back to some point where it'll perceive the bottom of the arrow. So there it is. So go ahead and construct your 3rd ray now. Again, this angle is not critical, but once you pick whatever that angle is, this one is, it has to be exactly the same, and then extend that reflected ray behind the mirror. Go ahead and do that now. All right, now we just need 1 more ray. I could go like this if I wanted to, but then it's going to get a little cluttered, so since there's plenty of space here, I'll go this way with this ray. The exact angle doesn't matter yet. So there is 4 incident. And now I have to reflect that off the mirror. So I will use my protractor again. Line that up there. And then line the back edge of the protractor up with the mirror. That looks pretty good. So now I will figure out, well, I'll mark the normal. And then I'll figure out the incident angle here. This is 10 degrees right here, and then mine looks like one beyond. So it's 11 degrees is my incident angle. So I have to make my reflected angle at 11 degrees. Here's 10. I'll go one beyond that. There's 11 degrees. All right, so time to construct the normal. And time to construct the reflected ray. So, okay, this is 4 reflected. And then again, my brain, what it does is it will, when it receives these 2 rays into my eyes, it'll trace these back and believe that the object that created these rays originated where they meet, just like you saw when I did that little demonstration yesterday where my eyes crossed looking at the penny. And there it is. That's where my brain believes the tail of the arrow is. So go ahead, construct this 4th ray now. Again, this actual angle doesn't matter in the beginning, but once you set this angle, the reflected must be exact to the best of your ability. So construct the ray and then take the reflected one, trace it back behind the mirror. So go ahead and do that now. Okay, so now the question is, where is the image of the arrow? Well, we got where the head is, we got where the tail is, so we can fill in the pieces now like this. This is where, all right, let's see, maybe we'll make a precise point there and there. So like this. There is the image. Now, maybe to emphasize that, I'll trace it with a marker. Not necessary for you. Let's see, what color would I take? Red, I already have red. Maybe a nice rich blue. Let's see. Let's try this one. There. Just like we saw earlier when I had the arrow in front of the actual mirror in the previous demonstration. So go ahead, fill in this arrowhead, label it image. You could even put head and tail if you want for those labels. Go ahead and do that now. All right, now what I'm going to do is go to the chalkboard and summarize everything that we learned about the conclusions we can draw from our ray tracing and our demonstrations earlier. So now what we're going to do is continue with the notes underneath this diagram here in your notebook. But I just want to point out that maybe if you're looking at your diagram, it doesn't look as nice as this. Maybe this image arrow is a little bit off. It doesn't look exactly the same size and orientation as the object. And that's okay, because again, this is all based on drawing, and a slight inaccuracy in any one of these 4 rays over here could compound itself and you could get a very funny looking image. So if that was the case for you, don't panic. What's going to be more important are the concepts that I'm going to summarize in terms of the regions, and also I'm going to show you a nice shortcut that gives you the answers like this with much less effort using the concepts that we're just going to write down now. All right, so here's the summary of what we saw with the mirror in the beginning of this video and with the ray tracing. So the image characteristics, this I didn't mention yet, but the image is what we call virtual and not real. What do we mean by that? A real image can be projected on a screen. A virtual can't be projected onto a screen like a movie or even a camera. When you take a photo, the image is projected onto the sensors in there. So that those are both real image. This is not. It only exists in our minds when we look at the mirror, then inside the mirror behind it, our mind creates that image from the perceptions of the way we receive the rays. The second thing, the second summary statement is that the image is right side up. If it's upside down in optics, they typically say inverted. You could say upside down, but just know that the word they use typically is inverted. The image is reversed. What we mean by that is left is right, right is left. Words appear backwards, for example. You may notice, you may have noticed, that when you're driving around, you look at an ambulance. The word ambulance is written on the hood, but backwards. The reason for that is that they want people to, when they look in the rearview mirror, they hear sirens. What's that noise? They look, and they don't want the word ambulance to appear in your mirror backwards, so they write it backwards on the hood, so that when the mirror reverses it, you see ambulance, and there's no thinking, and you can respond more quickly to the word because it appears correctly for you in your mirror. So backwards, reversed here. The fourth thing is that the image is the same distance behind the mirror as the object is in front of the mirror, and the way we would write that with an equation is d image equals d object. Technically, there's a minus sign there if you were studying optics in higher level courses. But basically, that's the equation way to state this. So I'll create a pause. Go ahead and copy these notes down. All right, continuing on, fifth point. The image is the same size as the object. Now, to quantify that, the changes in size, what physicists do is they define something called magnification, symbol capital M. And what it is it's a ratio of the height of the image over the height of the object. I didn't write image and object, but you could if you want. I just did a little shorter notation like that. And in our example, when the image is the same size and it's right side up, technically we could express that by writing both those things, that the magnification is +1. Positive meaning the image is the same orientation, not upside down, and it's the same size. The ratio of heights is the same. So some other examples of magnifications, if you had a magnification of +0.5, what that means, the positive is the image is right side up, the 0.5 means the object's half the size. 0.1, it would be 10% of the original. So kind of makes sense. Now, if you had a magnification of -2, the negative would be expressing that the image is actually upside down. And the 2 expressing the image is twice as big as the original object. So I'll create a pause. Go ahead and write these facts down. All right. So as I said just a second ago, there is a shorter way to find images in plane mirrors, a shortcut instead of the ray tracing. So let me make some room, and I'll show you that technique. Okay, so let's suppose we've got the letter L in front of a mirror like this. And so how can we determine the image? Well, in this case, if we did ray tracing, we'd have 3 points to ray trace 6 rays. Oh, that'd be even more tedious. However, what we could do is use some of the facts that I just erased. For example, if I label these points A, B, and C, I could find those points simply by the fact that A, the image of A, will be exactly the same number of centimeters this is in front of the mirror, the same exact centimeters behind the mirror. So I see about 19 centimeters. Yours in your notebook will be different. Use a ruler. Maybe you measure 1.5 centimeters. Whatever that distance is, I'm going to make the image of A the same distance behind the mirror. So I'm going to go, what did I say, 19? Yeah, 19 centimeters. And I'll put a dot. And this is not where A is. It's the image of A, so I'll put like an A prime. Okay, and I'm going to do the same with the other points. B is also 19 centimeters in front of the mirror, so I'm going to go 19 centimeters behind the mirror. And there is B prime. endpoint C reflects behind the mirror. Where? Well, 6 centimeters in front of the mirror, so it'll be 6 centimeters behind the mirror. So there's what I'm going to call C prime. And then the rest of the L I can fill in, draw down and over. Down from A to B, over to C. There is the image. So I'll create a pause. You copy this example down. All right, so my original idea was that I would have example 2 here, but I got a little carried away and made my example 1 too big, so let me make room for example 2. All right, now I put a triangle in front of a mirror, a plane mirror. Again, if I want to do ray tracing, I need to ray trace 3 points, 6 total rays, 2 for each. Too tedious. Let's just use the facts of what we know about images in a mirror, label these and reflect them according to the principles that we know about plane mirrors. So for example, A is, it's about 24.5 centimeters in front of the mirror. The image of A will be 24.5 behind the mirror. And I'll label this A prime instead of A. B is 4.5 centimeters in front of the mirror. The image of B will be 4.5 centimeters behind the mirror. So I'll label this B prime. And C is about 11.5 centimeters in front of the mirror. C prime will be 11.5 centimeters behind the mirror. C prime. And the rest of the pieces we could fill in. We go from A to B to C and back to A. So let's do that here. A to B to C, back to A. And there is the image. All right, so let me create a pause to give you a chance to copy this example down. Okay, so 2 examples is enough, I think. I think you get the idea. Label points, reflect them in the mirror using the distances, and then fill in the rest of the pieces. All right, so that's the second video, our second video on reflection. Today we were locating images in a mirror, which we often represent objects by arrows, and then ray trace for the 2 points in question, figure out where they are, and then fill in the rest of the pieces, and that's the image inside the mirror. And then this shortcut, instead of ray tracing, we could just go directly to measuring to find the images. So make sure you can do at least the shortcut, at least be able to trace 1 ray accurately reflected in a mirror. That's part of the Regents curriculum. And then look over those 5 concepts about images in plane mirrors. All right, so I hope you enjoyed the physics. I hope you enjoyed the video. I'll see you in the next physics video.